which occurred and 3 deaths which occurred in UK for the last 4 years, and in the overgrown vegetation has been contributing. What do overgrown vegetation does? Firstly, it obstructs driver view. Secondly, it obstructs critical road signs, which are very valuable for a driver. And third, it can also damage infrastructure. So all these 3 things, it's directly taxpayers' money, which in the third point, damaging infrastructure, which goes waste for lines or putting up extra signs where so many are not needed. So for this research, we have 3 objectives. First is to investigate existing methods for tackling this issue and identifying what are its limitations. Second is to identify information requirements for vegetation management, which is the key thing. And the third thing is how can we fulfill these information requirement to set up a digital twin. The methodology is a mixed methodology. So first we had some expert interviews, and we also read literature on overgrown vegetation. We identified the current methods and realized their drawbacks. Then we established information requirements, validated them with the experts, and then finally we proposed a new solution of how we can fulfill some of these requirements and demonstrate a proposed solution. I will be talking about this in a while. So information requirements, first thing, proposed solution, second thing, and demonstration. So BPMN, which is also known as Business Process Modeling and Notation, have been used to establish the existing process of managing roadside vegetation. This study is in the context of National Highways UK. So the existing process, if you can see, there are people who contribute to the process in the rows and the phases on the columns. So we have road inspector, program manager, and then road repair contractor, which are currently. And this process is relatively simple. The inspector goes, as he receives confirmation from program manager to do an inspection. He does a visual condition survey, sends inputs like image data and location data back in written form or through an app, and then this overgrown instance is recorded, and the vegetation control team then gives job to a contractor to clear all these. Now, why information requirements we need on first place? Information requirements for any digital twin are the backbone of those. So, to create product models, which comprises of ontological models like reference data libraries and foundation data model, we require information requirements for all of these. Once we have these information requirements, our physical twin and digital twin will be really connected based on these requirements, and we can take autonomous decisions. So here is what we finally led us to the requirements part. So we have roadside assets, which is the vegetation here. We have stages for vegetation, like what is the first stage is survey technology selection stage. Second is project specific information, overgrown vegetation instances, and vegetation control technology. All these 4 stages, we have multiple factors contributing to those stages, and each factor is contributed by many information requirements. So this is kind of the key backbone to the DT, which is going to be there. So currently, the information requirements which we have scoped for this research is on like location of overgrowth, the size and dimensions of overgrowth, the type of vegetation, and priority. And for the existing approach, all of these either don't exist or are in manual form. So the concept for us is that if there is a overgrown vegetation on the road, the ideal case should be that we need a vegetation-free envelope along the roadside, and once we detect it, we can use road markings to detect it, and once it is detected, autonomous vehicles can go there and clear it. So this is our proposed solution. I'll go through all the steps one by one. It comprises of a computer vision pipeline. So the first step is, if you see, we collected data using an iPhone camera using an on-the-go video. The image is not very clear, but that was our input as an original video frame. Second is we segmented and classified it using a detectron 2 algorithm, which detects the roadside vegetation away from the pavement and the grass. And the third thing is conversion to grayscale. We converted the image to grayscale. Now we wanted to use roadside markings for detecting overgrown vegetation. So we did image partition, and then we applied threshold for intensity filtering. We clustered using DB scan and detected the left side road marking. Finally, once we had that, we projected the road marking to the vegetation, and using PyTorch, we got the depth map from the image, and we detected what part of the overgrowth is outside. Then we measured this overgrowth relatively based on the dimensions of the road, from road marking to road marking at the same depth, and it was found around 44% of overgrowth for the roadway. So what is the difference between the previous method and this method? We have fulfilled some of these information requirements. So location of overgrowth is based on the GPS signal. The size and dimension of overgrowth are relative overgrowth dimensions. Initially, the airline inspector had to approximately say how big is that. Now we have some relative indication of how big is the overgrowth. Automatic vegetation type detection, so that the algorithm detects whether it is a grass, shrub, tree, or anything else. And priority, based on the location as well as based on the size, we can give automatic priority for maintenance team to go and clear it. So our conclusions are that the existing process depends on a lot of subjectivity and reliance. The digital twin-based approach can help us in fulfilling key information requirements, and the widespread adoption of this approach will take place when connected autonomous vehicles are there, which will be going through road on a regular basis and collecting real-time data. Some of the future work which include is what will change if we switch the data acquisition method from 2D to 3D. Right now I showed you an image-based example, but currently we are working on a 3D-based input from a mobile laser scanner from camera. So how the table of requirements will change, what will happen. So we found out that the 3D information requirements can give us the full geometry of the overgrowth, like the length, breadth, dimension, not just the relative 2D can do. And secondly, how can we have these requirements to link with other road assets? So for example, traffic signs are very closely linked with roadside vegetation. So what about traffic signs we can use to integrate in roadside vegetation data requirements? European Union Horizon 2020 under the Paris Scotta Curie grant. Thank you.
So any questions for our amazing three presenters?
Yes, please. Yes, please.
Anyone pass?
Hello? Hello?
Seems like we have quite a bit of technical issue this afternoon, right? Hopefully the rest of the session will run smooth.
Hello? Hello? Doesn't work. I can...
Yeah, we can hear you.
Yeah, okay. For the third speaker, yeah, you mentioned ontologies. Can you say some words about ontologies and vegetation?
Okay, so as ontology, we are looking at national highways, what they have been using as their maintenance tool. So they used a tool called Confirm. In the ontologies, they have it is on a very high level. We have roads, we have in roads environment, we have multiple road assets like road markings, traffic signs, Roadside vegetation is one part of it, and then we have drainages, and these all comes under road. So what we are going to do is we are going to create foundation data model for each of these assets connecting to the ontologies which national highways currently have for individual road assets.
It's something they already have.
They already have a basic version of it, as I showed, like image data, they have they have the basic requirements. But what we did in this paper was generate additional requirements using that. Yeah.
Thank you.
Yeah.
Hello.
Please, there's a question here. Do you want to just ask without? Yeah, sure, please.
Hello.
Information. Yeah. 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 Okay, so for this research, we wanted to collect data, and we wanted to collect data to validate the solutions which we are proposing. So hence we used mobile-based video. But professionally, this should be done by video from data sensing device. But what we did was we have multiple inputs in that M70 laser scanner, which we have with Kodiak. Kodiak is a company which do data collection on our behalf. So they have an MX70 mounted onto a car, and they run that car all through the road. So they kind of capture 40 kilometers of road data set. By the way, we also published a road data set, which is known as the CAM data set, the Cambridge Highway data set. It is about 40 kilometers of road, annotated among all the classes, which have been there in the roadside assets, which I have mentioned. So using that is the second stage, which is the future work, which I have currently done after I have submitted this paper. So in 3D, with 3D data, we have a trade-off to consider. So the data acquisition for a 2D is just a 2D image, like a videographic film going from one angle. And it is not so costly. It is just, you need a sensor which can collect our 2D data. But for a 3D data, the MX70 actually costs a bit. While we are getting the whole 3D profile of the overgrowth vegetation, we are spending too much on the costs. So there is a trade-off to consider. Do we require that additional level of absolute details of dimensions in breadth, volume, and density? Or we are okay with the relative indication, if X is the road width, what percentage of X is the overgrowth vegetation? So that trade-off we need to consider. Thank you for the question. Yeah.
Thank you. I think we have just time for one more question.
Yeah, currently we haven't included carbon emissions in the whole life cycle management, but we also have another team, another research group in our teams that focus on the carbon emissions, and I think it would be easy to combine them together if the quantities of steel reinforcement can be calculated or measured exactly. Yeah.
Thank you so much for presenting your research work, and let's give another round of applause to our presenters.